Tonight, we descend into the Great Red Spot, a storm larger than Earth, turning quietly for centuries. Welcome to the Orbit for Sleep channel. Let gravity take over and drift gently towards sleep. You drift closer to Jupiter, and the planet slowly fills your view. Bands of clouds stretch across its surface like wide rivers of color, moving at different speeds, never settling. Near the southern hemisphere, one feature stands out. A vast oval shape rotates calmly, distinct from everything around it. This is not a single cloud, nor a passing disturbance. It is a storm larger than Earth, turning steadily in the same place. The Great Red Spot is a giant atmospheric vortex, a long-lived rotating system of wind and clouds. On Earth, storms appear, grow intense, and fade away within days or weeks. Even the strongest hurricanes lose energy when they move over land or cooler water. Jupiter has no solid surface and no oceans. Its atmosphere is deep, continuous, and fueled from below by internal heat. This allows storms to persist far longer than anything familiar on Earth. The scale of the Great Red Spot becomes clearer when compared to everyday experience. Earth's largest hurricanes can span several hundred kilometers. The Great Red Spot once measured more than 40,000 kilometers across, wide enough to swallow Earth whole. Winds along its outer edges reach speeds faster than a commercial jet, yet the storm itself rotates with a steady, almost unhurried rhythm. This contrast between violence and stability defines the storm's character. Historical records show that astronomers noticed this feature as early as the 17th century. Telescopes of that era revealed a persistent oval marking on Jupiter's surface. Over centuries of observation, the storm remained. Spacecraft in the late 20th century confirmed that the same structure continues to exist today. Few natural phenomena in the solar system display this level of endurance. The reason the storm never truly ends lies in Jupiter's energy balance. Heat rises from deep within the planet, replacing energy lost at higher altitudes. Smaller storms drift nearby and sometimes merge into the Great Red Spot, feeding it additional momentum. This process resembles traffic entering a circular highway interchange, where incoming motion sustains the overall flow rather than disrupting it. Seen from a distance, the storm appears calm and contained. In reality, it represents a planetary system operating on a scale that far exceeds human weather. The Great Red Spot is not remarkable because it is violent, but because it is stable. It demonstrates how different the rules of nature become when size, energy, and time stretch beyond familiar limits. The motion of the storm continues without interruption. After noticing its immense size and steady rotation, attention settles on what this structure truly represents. The Great Red Spot is not a surface feature. It exists entirely within Jupiter's atmosphere, suspended in layers of gas with no solid ground beneath it. At its core, the Great Red Spot is a high-pressure system. Air flows inward, begins to rotate due to the planet's rapid spin, and becomes organized into a vast circulating pattern. This behavior follows the same physical rules that govern rotating systems on Earth, such as whirlpools in water or the spiral motion of cream spreading in a cup of coffee. The difference lies in scale and duration. Jupiter rotates once in roughly 10 hours. This fast rotation strengthens what scientists call the Coriolis effect, a force that causes moving air to curve rather than travel in straight lines. On Earth, this effect shapes trade winds and hurricanes. On Jupiter, it organizes entire bands of clouds and allows storms like the Great Red Spot to maintain a stable, oval shape for extremely long periods. The storm spans multiple atmospheric layers. At the top, visible clouds reflect sunlight, creating the familiar red appearance. Below that, deeper layers of gas continue to circulate, hidden from view. Measurements from spacecraft indicate that the storm extends hundreds of kilometers downward. This vertical depth means the Great Red Spot is not a thin surface swirl, but a three-dimensional structure embedded deep within the planet. Unlike storms on Earth, the Great Red Spot does not rely on warm oceans for energy. Jupiter generates heat internally as it slowly contracts under its own gravity. That heat rises through the atmosphere, providing a continuous energy source. This process can be compared to a room warmed from below by a heated floor, where gentle upward motion never fully stops. Over time, the storm behaves like a self-contained system. It absorbs energy from surrounding winds, deflects smaller storms, and maintains its rotation. Rather than breaking apart, it settles into a long-lasting balance between incoming and outgoing energy. In this way, the Great Red Spot functions less like a temporary weather event and more like a permanent feature of Jupiter's atmospheric circulation. Once the nature of the Great Red Spot becomes clear as a deep atmospheric system, its most striking trait comes into focus: its persistence. This storm is not measured in hours or seasons. Its lifespan is counted across generations of observers. The earliest reliable records date to the 17th century, when astronomers using early telescopes noticed a large, oval-shaped feature on Jupiter's surface. Drawings from that period show a mark in roughly the same region where the Great Red Spot is seen today. While the exact continuity of the earliest observations cannot be proven with absolute certainty, the evidence strongly suggests a single, long-lived storm rather than a series of short-lived ones. By the 19th century, telescopic observations became more precise. Astronomers consistently recorded the storm's position, shape, and rotation. Unlike smaller features that appeared and vanished over time, this one remained. Its slow drift in longitude could be tracked, much like following a buoy floating in a powerful but steady current. Spacecraft observations in the 20th century confirmed what centuries of ground-based observation had implied. The same massive vortex was still active. Data revealed not only its surface appearance, but also its depth and wind structure. This continuity across observation methods reinforced the conclusion that the Great Red Spot is among the longest-lasting storms ever observed in the solar system. Comparisons with Earth's weather highlight how unusual this is. Even stable climate patterns on Earth shift over decades. A single storm surviving longer than a human lifetime is unheard of. On Jupiter, however, the atmosphere changes slowly, and the energy driving large-scale motion is constantly replenished from within. The Great Red Spot's age is not merely a curiosity. Its endurance provides scientists with a natural laboratory for studying long-term atmospheric stability. It shows how, under the right conditions, motion can persist without collapsing into chaos. In this way, the storm becomes a quiet record of time itself, turning steadily while centuries pass beneath it. As centuries pass and the great red spot continues to endure, its motion becomes the next point of quiet attention. The storm does not drift randomly or spin without order. Its rotation follows clear physical rules, shaped by Jupiter's size, speed, and atmosphere. Jupiter rotates extremely fast, completing one full turn in about 10 hours. This rapid spin strongly influences how air moves across the planet. Any large flow of gas is gently curved as it travels, guided by what scientists describe as the Coriolis effect. On Earth, this effect causes large storms to rotate and gives hurricanes their familiar spiral form. On Jupiter, the same principle operates on a much larger and more stable scale. The Great Red Spot rotates counterclockwise, marking it as a high-pressure system in Jupiter's southern hemisphere. Air flows inward toward the center of the storm, then turns and circulates rather than rising and dispersing. This inward motion creates a compact, long-lasting vortex instead of a short-lived burst of activity. The absence of a solid surface below prevents friction from slowing the motion. Surrounding the storm are powerful jet streams moving in opposite directions. One flows eastward above the Great Red Spot, while another flows westward below it. These opposing currents act like moving walls, confining the storm and helping it maintain its shape. The effect can be compared to a spinning object held steady between two conveyor belts, moving in opposite directions. Energy within the storm circulates rather than escaping. As air moves around the vortex, it redistributes heat and momentum internally. This balance prevents the storm from collapsing or spreading out. Instead of fading, the rotation settles into a steady pattern that can persist for centuries. The way the Great Red Spot rotates reveals how motion behaves on a planet built almost entirely of gas. It shows that when rotation is fast, energy is abundant and resistance is low. Movement does not easily stop. In such environments, time stretches, patterns stabilize, and storms become enduring features rather than passing events. As the rotation of the Great Red Spot remains steady, another layer of understanding settles in. Rotation alone does not explain endurance. What allows this storm to continue without fading is a quiet balance between energy gained and energy lost. Jupiter is not a passive planet. Deep beneath its cloud tops, the planet releases heat, left over from its formation and from slow gravitational contraction. This internal heat rises through the atmosphere, creating constant upward motion. Unlike Earth, where sunlight is the main driver of weather, Jupiter's storms are powered largely from below. The Great Red Spot draws on this internal energy, allowing it to renew itself continuously. Smaller storms play an important role in this process. Around the Great Red Spot, compact vortices regularly form and drift nearby. When some of these smaller systems approach the larger storm, they are absorbed into its circulation. Their momentum and energy merge with the main vortex rather than disrupting it. This can be compared to small streams feeding into a wide, slow-moving river, strengthening its flow without changing its course. Energy loss still occurs. Winds gradually radiate heat into surrounding space, and turbulence slowly drains motion. However, the rate of energy input closely matches the rate of loss. This balance prevents collapse. Instead of weakening, the storm adjusts its size and shape to maintain stability over long periods of time. The surrounding jet streams also contribute to survival. They act as barriers that reduce energy leakage and limit how much the storm can spread outward. Confined but not compressed, the Great Red Spot remains dynamically active while structurally stable. Together, internal heat, absorbed storms, and atmospheric confinement create a system that sustains itself. The Great Red Spot remains alive, not because it resists change, but because it adapts continuously. Its survival reflects a broader truth of planetary systems. When energy flows steadily and structures are allowed to adjust, motion can persist far longer than intuition suggests. With the survival of the Great Red Spot understood, attention naturally shifts downward. Beneath the visible red clouds lies a complex, layered atmosphere that gives the storm its depth and strength. What appears as a single surface feature is only the uppermost expression of a much thicker structure. Jupiter's atmosphere is arranged in layers, defined by temperature, pressure, and composition. At the highest visible levels, clouds are formed primarily from ammonia ices. These thin clouds reflect sunlight and create the familiar bands seen through telescopes. The red coloration of the Great Red Spot is concentrated here, where sunlight interacts with chemical compounds altered by radiation. Below this upper layer, pressure increases steadily. Ammonia clouds give way to deeper clouds made of ammonium hydrosulfide. And farther down, water clouds begin to dominate. These layers are not sharply separated. They blend gradually, much like layers of fog and mist forming at different heights on a cold morning. Measurements from spacecraft indicate that the Great Red Spot extends hundreds of kilometers beneath the visible cloud tops. Winds continue to circulate well below the red surface, confirming that the storm is a deep atmospheric system rather than a shallow disturbance. The deeper the flow, the more resistant the storm becomes to surface-level disruption. Heat rising from Jupiter's interior passes through these layers, fueling slow upward motion. As warm gas ascends and cooler gas sinks, energy is redistributed throughout the storm. This process resembles air circulating in a large building warmed from below, where movement continues even when the space appears calm. The layered atmosphere beneath the Great Red Spot explains its remarkable stability. Instead of existing at a single height, the storm is anchored across multiple atmospheric levels. This vertical structure allows it to absorb energy, adjust internally, and remain coherent over long periods of time. Quietly embedded within the vast depth of Jupiter's gaseous envelope. With the layered depth of the Great Red Spot in view, motion within that structure becomes easier to sense. The storm is not a uniform spin. Wind speeds change with height, distance from the center, and interaction with surrounding flows. At the outer edges of the Great Red Spot, winds reach their greatest speeds. Measurements show velocities exceeding 400 kilometers per hour, faster than any sustained wind on Earth. These fast-moving outer bands act like a protective ring, helping the storm maintain its shape. Closer to the center, motion slows and becomes more organized, creating a stable core rather than chaotic turbulence. This pattern resembles everyday motion in familiar systems. Traffic on a circular highway interchange moves fastest along the outer lanes, while cars near the center loop move more slowly and predictably. The Great Red Spot follows the same principle, scaled up to planetary size. Wind speed also varies vertically. Near the visible cloud tops, motion is strong and clearly defined. Deeper layers move more slowly, but remain tightly connected to the overall circulation. This vertical coupling allows momentum to be shared throughout the storm, preventing surface winds from dissipating too quickly. Surrounding jet streams further influence these speeds. As fast atmospheric currents pass above and below the Great Red Spot, they shear against its outer edges. Rather than tearing the storm apart, this interaction sharpens the boundary and reinforces the high-speed outer flow, much like steady riverbanks guiding a powerful current. The result is a system where speed and stability coexist. Fast winds provide structure, while slower internal motion preserves balance. This layered pattern of movement helps explain how the Great Red Spot remains coherent across centuries, maintaining strength without collapsing into disorder, quietly rotating within Jupiter's vast atmosphere. As wind speeds trace the motion of the Great Red Spot, a quieter process unfolds beneath that movement. Energy flows continuously through the storm, guiding how long it can remain active. This flow is not sudden or explosive. It is slow, persistent, and deeply embedded in Jupiter's atmosphere. Unlike Earth, where sunlight drives most weather systems, Jupiter generates a large portion of its energy internally. Heat rises from the planet's interior as Jupiter slowly releases energy left from its formation. This upward flow passes through the atmosphere and enters the Great Red Spot from below, supplying warmth that sustains motion over long periods of time. Inside the storm, warm gas gradually ascends, while cooler gas sinks. This circulation redistributes energy rather than allowing it to escape quickly. The process can be compared to a pot of water kept just below boiling on a stove. Gentle convection continues, even though the surface appears calm and unchanged. This internal heat flow works together with rotation. As energy moves upward, it is redirected sideways by the planet's rapid spin. Heat becomes motion, and motion becomes organized rotation. Instead of dissipating, energy is stored within the storm's layered structure and released slowly through friction and radiation. Measurements show that the Great Red Spot radiates heat into space at a rate closely balanced by the energy it receives. When losses increase, internal circulation adjusts. When gains rise, the storm subtly changes size or speed. These adjustments occur gradually, without sudden collapse or runaway growth. The steady flow of heat explains why the Great Red Spot behaves less like a temporary weather event and more like a stable climate system. Energy does not surge or vanish. It circulates, settles, and renews itself. Within this balance, the storm continues its slow rotation, sustained by the deep warmth of Jupiter itself. As heat and motion circulate within the Great Red Spot, its color quietly draws attention. Among Jupiter's pale bands and white clouds, this storm stands apart with a deep red tone that has remained recognizable for centuries. The color is not decorative. It reflects chemistry shaped by altitude, sunlight, and time. At the highest levels of the storm, clouds are composed mainly of ammonia ice. On their own, These clouds would appear white, much like thin cirrus clouds on Earth. The red color emerges when these materials are altered by radiation from the Sun and from Jupiter's magnetosphere. Ultraviolet light breaks apart simple molecules, allowing them to recombine into more complex compounds. Scientists refer to these altered materials as chromophores, substances that absorb certain wavelengths of light and reflect others. In the Great Red Spot, chromophores absorb blue and violet light while reflecting red tones back into space. The result is a color that deepens over time as exposure continues. This process resembles everyday changes seen on Earth. An apple left in sunlight gradually darkens as its surface chemistry changes. Metal exposed to air slowly develops rust. In both cases, the transformation is slow, cumulative, and visible only over extended periods. The Great Red Spot undergoes a similar chemical aging written across its cloud tops. Altitude plays a key role. The storm's powerful upwelling lifts material from deeper layers into higher regions where radiation is strongest. Once there, the compounds are altered and spread by the storm's circulation. If this material were to sink back down, its color would fade. Continued upward motion keeps the red tones renewed. The color of the Great Red Spot is therefore a record of ongoing activity. It signals that the storm is not only moving, but actively exchanging material between depths and heights. The red hue marks a place where chemistry, energy, and time converge, leaving a visible trace of processes unfolding far beyond human scale. As the color and internal activity of the Great Red Spot become clear, its relationship with the surrounding atmosphere comes into view. The storm does not exist in isolation. Jupiter's atmosphere is crowded with smaller vortices that drift, collide, and evolve alongside it. These smaller storms form within the same banded cloud system that feeds the Great Red Spot. Some are short-lived, while others persist for months or years. As they move along Jupiter's powerful jet streams, their paths occasionally bring them close to the larger vortex. When a small storm approaches the Great Red Spot, several outcomes are possible. Some are deflected and slide past its outer edge, their paths gently altered. Others are drawn inward and absorbed. During absorption, the smaller vortex stretches, loses its individual structure, and merges into the larger circulation. Its energy and momentum do not disappear. They are redistributed within the Great Red Spot. This interaction resembles small eddies joining a wide river. Each eddy contributes motion without changing the overall direction of the flow. Rather than destabilizing the system, these encounters often strengthen it, adding fresh energy to the storm's outer layers. Observations from spacecraft in the late 20th century documented multiple such mergers. After absorbing nearby storms, the Great Red Spot sometimes changed shape temporarily, becoming slightly more elongated or compact. Over time, it settled back into a stable form, adjusted but intact. These interactions reveal an important aspect of the storm's behavior. The Great Red Spot survives not by resisting its environment, but by engaging with it. By exchanging energy with surrounding storms, it remains connected to the broader circulation of Jupiter's atmosphere. The storm persists as part of a dynamic system, sustained by continual interaction rather than isolation. After After tracing the Great Red Spot through layers of gas and surrounding storms, the scale of the system invites a quieter comparison. When imagined against Earth's familiar surface, the storm gains a different kind of clarity, one shaped by places, distances, and patterns humans know well. If the Great Red Spot were placed over Earth, it would stretch across entire continents. Its width would span from one ocean basin to another, covering regions that normally experience very different climates. Areas that, on Earth, would be separated by thousands of kilometers of land and sea would instead fall under a single rotating system. What appears as a compact oval on Jupiter would become a planetary feature on Earth, visible from orbit as a dominant structure rather than a regional storm. From space, the contrast would be immediate. Satellites that usually track moving cloud systems would observe a single feature that barely shifts position. Instead of watching storms form, travel, and dissolve, instruments would record the slow, continuous rotation of the same atmospheric structure, day after day, year after year. From the ground, the sky would look unfamiliar. Clouds would not pass overhead in changing patterns tied to daily weather. Instead, the same rotating system would remain fixed in place for years. Winds near the edges would move faster than any recorded terrestrial storm, while the center would appear calmer, enclosed by continuous motion extending far beyond the horizon. The sense of direction itself would feel altered, as air followed curved paths rather than flowing in straight lines. The passage of time would feel different as well. On Earth, weather marks the rhythm of days and seasons, signaling change through temperature shifts, storms, and clear intervals. Under a storm like the Great Red Spot, the environment would change slowly, almost imperceptibly. Conditions would persist rather than cycle. The storm would not announce itself with sudden arrival or departure. It would simply remain, becoming part of the background of daily experience. This contrast highlights the key difference between Earth and Jupiter. Earth's weather is shaped by oceans, land, and sunlight, all of which introduce variation and interruption. Continents disrupt winds, mountains redirect air, and temperature differences drive constant change. Jupiter's atmosphere offers no such boundaries. Without solid surfaces to weaken it, a storm of this scale can persist without losing its identity. Seen through an earthly lens, the Great Red Spot becomes less abstract. It shifts from a distant astronomical feature into a concrete reminder of how scale reshapes experience. When size, energy, and time grow large enough, weather stops behaving like a temporary event and begins to resemble a permanent condition of the planet itself. With the Great Red Spot now placed against Earth's familiar scale, comparison becomes unavoidable. Although hurricanes on Earth and Jupiter's giant storm follow the same physical laws, the environments that shape them lead to very different outcomes. On Earth, hurricanes form above warm oceans. Sunlight heats the surface water, causing warm, moist air to rise. As this air ascends, it releases energy that drives rotation and wind. When a hurricane moves over land or cooler water, its energy source weakens. Friction with the ground disrupts circulation, and the storm gradually fades. Even the most powerful hurricanes are temporary systems. The Great Red Spot forms under different conditions. Jupiter has no oceans and no solid surface. Its atmosphere extends downward for thousands of kilometers, uninterrupted by continents or mountains. Energy comes not from sunlight alone, but from heat rising from deep within the planet. This continuous supply allows the storm to persist without encountering barriers that would weaken it. Wind speeds also reflect this difference. Earth's strongest hurricanes reach wind speeds capable of reshaping coastlines and cities, yet these extremes are short-lived. In the Great Red Spot, comparable or greater wind speeds remain stable over long periods. Instead of peaking and collapsing, motion settles into a sustained pattern. Structure further separates the two systems. Hurricanes on Earth are vertically limited, extending only a short distance upward through the atmosphere. The Great Red Spot reaches far deeper, anchoring itself across multiple atmospheric layers. This depth gives the storm resilience, allowing it to absorb disturbances rather than break apart. Time is perhaps the clearest distinction. An Earth hurricane is remembered as an event. It has a beginning, an intensification, and an end. The Great Red Spot functions more like a climate feature. It does not arrive or depart. It exists as a long-term condition of Jupiter's atmosphere, shaped by scale rather than chance. This comparison reveals how familiar physics can lead to unfamiliar outcomes. When gravity, size, and energy operate on planetary scales, weather transforms. What is fleeting on Earth becomes enduring on Jupiter, showing how the same natural rules express themselves differently across worlds. After comparing Jupiter's Great Red Spot with storms on Earth, its broader significance becomes clearer. This single, long-lived vortex offers insight into how weather behaves when planetary conditions change. It shows that weather is not defined only by clouds and wind, but by the environment that surrounds them. One of the clearest lessons comes from scale. On Earth, weather systems are small compared to the planet itself. Oceans, continents, and mountains interrupt their motion. These boundaries limit how long storms can survive. On Jupiter, the atmosphere covers the entire planet without solid obstacles. When motion begins, there is little to stop it. As a result, weather systems can grow larger and last longer than intuition suggests. Energy sources also shape behavior. Earth's weather depends heavily on sunlight and surface temperature. When sunlight fades or surfaces cool, storms weaken. Jupiter reveals another pathway. Internal heat rising from deep within the planet can sustain motion continuously. This shows that weather does not require a surface or an ocean. It only requires a steady flow of energy. The Great Red Spot also demonstrates the importance of depth. Shallow systems are fragile. When disturbances affect them, they collapse. Deep systems, connected across many layers of atmosphere, absorb change and remain coherent. This principle applies beyond Jupiter. It helps scientists understand why some atmospheric patterns on Earth persist for decades, while others vanish quickly. Observation history reinforces this lesson. By tracking the same storm across centuries, scientists can test ideas about stability, circulation, and energy balance. Few natural laboratories allow such long-term study. The Great Red Spot provides evidence that weather can be a slow process, unfolding over timescales longer than human lives. Taken together, These insights reshape how planetary weather is understood. Storms are not merely temporary disturbances. Under the right conditions, they become structural features of a planet. Jupiter's Great Red Spot teaches that weather is an expression of planetary design, revealing how size, energy, and time quietly govern motion across worlds. After considering what the Great Red Spot reveals about planetary weather, attention turns toward human perception. Long before spacecraft and digital instruments, observers on Earth noticed this storm for a simple reason. It refused to blend into the background. Jupiter is bright and large in the night sky. Even early telescopes of the 17th century revealed its banded appearance. Most features shifted subtly from night to night, but one oval marking remained visible. Its size, contrast, and persistence made it stand out against the changing cloud bands around it. For early astronomers, this stability was unusual enough to record. At a time when planetary surfaces were expected to be static, a long-lasting atmospheric feature challenged assumptions. The storm appeared fixed, yet it changed slightly in shape and color. This combination of permanence and variation drew careful attention. Observers sketched its position repeatedly, not because it was dramatic, but because it was reliably present. The visibility of the Great Red Spot also benefited from Jupiter's rapid rotation. As the planet turned, the storm regularly came into view, returning with predictable timing. This repetition made it easier to recognize as the same structure rather than a coincidence of clouds. Over many observations, its identity became clear. Human perception favors patterns that endure. Just as familiar landmarks help orient travelers, the Great Red Spot became a reference point for studying Jupiter itself. By tracking its movement, astronomers could measure the planet's rotation and compare changes in atmospheric behavior over time. The storm was noticed not because it was violent, but because it was consistent. Its presence across generations of observers reflects a quiet truth about discovery. Phenomena that persist invite understanding. The Great Red Spot entered human awareness simply by remaining visible long enough for curiosity to settle and observation to continue. As human observation brings the Great Red Spot into focus, a broader question quietly emerges about life and its boundaries. This storm represents an environment where familiar biological assumptions no longer apply. By examining it, scientists gain insight into where life can exist and where it likely cannot. Life on Earth depends on a narrow balance of conditions. Stable temperatures, liquid water, moderate pressure, and long-term chemical consistency allow biological systems to form and persist. Within the Great Red Spot, these requirements are absent. Temperatures vary sharply with altitude, pressures increase rapidly with depth, and winds reach speeds that would disrupt even the simplest structures. Chemical conditions further limit possibility. Jupiter's atmosphere is dominated by hydrogen and helium, with traces of ammonia, methane, and water vapor. These substances exist under intense pressure and radiation. Ultraviolet light and charged particles continually alter molecular bonds, creating an environment hostile to complex, long-lasting chemistry. Motion itself presents a challenge. The Great Red Spot is defined by constant circulation. Material is lifted upward, pushed outward, and drawn downward again in repeating cycles. This perpetual movement leaves little opportunity for stable niches to form. On Earth, even extreme ecosystems rely on pockets of relative calm. In this storm, such stillness does not exist. Studying these limits helps refine the search for life beyond Earth. It shows that size and energy alone do not guarantee habitability. A planet or moon may be dynamic and long-lived, yet remain unsuitable for biology. Conditions must not only exist, but remain gentle enough for complex systems to endure. The Great Red Spot, therefore, serves as a boundary marker. It illustrates where planetary processes become too intense for life, as it is currently understood. By observing such extremes, scientists better define the narrow zones where biology can take hold, persist, and quietly evolve within the vast diversity of planetary environments. As attention shifts toward the future of the Great Red Spot, a subtle but important change comes into view. Over decades of observation, the storm has been gradually decreasing in size. This change is not sudden or dramatic. It unfolds slowly, almost quietly, across long spans of time. Measurements from telescopes and spacecraft show that the Great Red Spot was significantly wider in the past than it is today. In earlier centuries, it extended across a much larger portion of Jupiter's southern hemisphere. Modern observations reveal a more compact shape, even though the storm remains powerful and clearly defined. This shrinkage reflects changes in energy balance. While Jupiter continues to supply internal heat, the distribution of that energy can shift. The surrounding jet streams that help confine the storm also evolve. Small variations in their speed or position alter how much energy the Great Red Spot can retain. When less energy is captured, the storm adjusts by contracting rather than disappearing. Interactions with smaller storms also play a role. In the past, frequent mergers may have added momentum and mass to the system. As those interactions become less common, replenishment slows. The storm does not collapse. Instead, it settles into a smaller, more efficient configuration. This process resembles familiar patterns on Earth. Large, slow-moving systems often become more compact over time as external conditions change. A city may shrink in area, but remain active at its core. A river may narrow, yet continue to flow steadily. The Great Red Spot follows a similar principle, adapting its size to match available energy. The gradual reduction in scale does not signal an imminent end. It reflects adjustment rather than decay. The Great Red Spot remains a long-lived structure, changing shape while preserving identity. Its slow contraction offers a reminder that even the most persistent planetary features evolve, guided by balance rather than permanence. Following the slow contraction of the Great Red Spot, its long-term future comes into view. The storm is changing, but not in a way that suggests sudden disappearance. Instead, its evolution appears gradual, shaped by the same balancing forces that have sustained it for centuries. One possible outcome is continued reduction in size. As surrounding jet streams shift and energy transfer becomes less efficient, the storm may grow smaller while remaining active. In this scenario, the Great Red Spot would persist as a compact vortex rather than a vast oval, still recognizable but less prominent within Jupiter's atmosphere. Another possibility involves structural transformation. Large vortices on Jupiter, sometimes reorganize into multiple smaller storms. Rather than vanishing, the Great Red Spot could eventually divide into separate rotating systems, each carrying part of the original storm's momentum. This process would reflect redistribution rather than loss. Complete dissipation remains the least likely near-term outcome. Jupiter's internal heat continues to drive atmospheric motion, and the mechanisms that support long-lived storms remain in place. Without a fundamental change in energy flow, the conditions that allowed the Great Red Spot to exist would still be present. Time frames for these changes extend far beyond human experience. Decades of observation reveal trends, but centuries may be required to confirm outcomes. From a planetary perspective, slow transformation is the norm. Stability and change coexist, unfolding at a pace that resists immediacy. Whatever form it takes, the Great Red Spot's future will remain tied to Jupiter itself. The storm does not follow a fixed lifespan. It adapts to shifting conditions, maintaining motion as long as balance allows. Its eventual fate illustrates how planetary systems evolve, not through abrupt endings, but through continuous adjustment across immense spans of time. As the future of the Great Red Spot unfolds within Jupiter's atmosphere, its rarity becomes more apparent when viewed against a wider cosmic backdrop. Storms of this size and longevity are not common features of planetary systems. They require a precise combination of conditions that few worlds provide. First, a planet must be large enough to sustain a deep, continuous atmosphere. Small planets lose heat quickly and develop solid surfaces that disrupt long-lived circulation. Gas giants, by contrast, retain internal energy and lack hard boundaries. Even among them, not all display storms that persist for centuries. Rotation plays an equally important role. Jupiter spins rapidly, strengthening large-scale atmospheric organization. On slowly rotating planets, motion disperses before stable vortices can form. Without sufficient rotational influence, storms remain transient, unable to lock into enduring patterns. Energy supply further limits rarity. Long-lived storms require steady input over vast timescales. On Jupiter, internal heat rises continuously, feeding atmospheric motion. Planets that rely primarily on sunlight experience fluctuations that shorten storm lifespans. Consistency, rather than intensity, proves essential. Observations of other planets in our solar system reinforce this view. Saturn hosts large storms, but they appear and fade over decades. Neptune shows powerful vortices that migrate and vanish. None match the Great Red Spot's combination of size, stability, and age. Beyond the solar system, exoplanet studies suggest that gas giants with extreme atmospheres exist, but their weather remains difficult to observe directly. Even so, the conditions required for a storm like the Great Red Spot appear narrow. Its persistence reflects a rare alignment of mass, rotation, and energy. Seen on a universal scale, the Great Red Spot is not merely a feature of Jupiter. It represents a particular outcome among countless planetary possibilities. Its rarity underscores how small differences in planetary design can lead to dramatically different expressions of weather across the cosmos. As the rarity of the Great Red Spot becomes clear, its deeper significance lies in what it reveals about gas giants themselves. This single storm acts as a window into the fundamental nature of planets built almost entirely from gas. Gas giants differ from rocky planets in one essential way. They have no solid surface to mark a clear boundary between atmosphere and interior. Instead, pressure and temperature increase gradually with depth, creating a continuous transition rather than a fixed ground. The Great Red Spot exists within this continuity, shaped by forces that operate far below what can be directly observed. The storm shows that gas giants are not static spheres wrapped in clouds. They are dynamic systems where motion, heat, and structure are deeply connected. Internal heat rising from the planet's interior drives large-scale circulation. Rotation organizes that motion into bands, jets, and long-lived vortices. The Great Red Spot is one visible expression of this hidden machinery. Depth plays a defining role. On a gas giant, atmospheric features can extend hundreds or thousands of kilometers downward. This depth allows storms to anchor themselves, drawing stability from layers far beneath their visible tops. The Great Red Spot demonstrates how deep circulation can preserve structure even when surface conditions change. The storm also reveals how energy is managed on gas giants. Instead of releasing energy in brief bursts, these planets distribute it gradually through broad atmospheric flows. This slow redistribution favors persistence over intensity. The result is weather that evolves patiently rather than dramatically. Taken together, these traits redefine what a planet can be. Gas giants are not worlds with weather layered on top. Their weather is inseparable from the planet itself. The Great Red Spot makes this clear by showing how atmosphere, interior, and motion merge into a single, continuous system that shapes the planet from within. As the Great Red Spot is placed within the broader context of gas giants and cosmic rarity, its final significance settles into view. The storm serves as a quiet reminder that planets, though governed by the same physical laws, can express those laws in profoundly different ways. From Earth, weather is temporary. It arrives, intensifies, and fades, shaped by land, oceans, and sunlight. Familiar rhythms define expectation. On Jupiter, the same principles of motion, heat, and rotation unfold without interruption. Without solid boundaries, atmospheric behavior stretches across vast distances and long spans of time. The Great Red Spot illustrates how scale reshapes meaning. What would be a destructive event on Earth becomes a stable condition on another world. Wind, heat, and rotation do not disappear, they reorganize. In doing so, they create patterns that endure rather than resolve. This contrast invites a broader understanding of planetary diversity. A planet is not simply a location in space, it is a system shaped by mass, composition, energy flow, and time. Small differences in these factors lead to worlds that behave in ways both familiar and entirely unfamiliar. Seen this way, the Great Red Spot is not an anomaly to be explained away. It is a natural outcome of Jupiter's design. The storm reveals how deeply a planet's identity is tied to its internal processes, not just its appearance. In observing such a feature, perspective quietly shifts. Earth's weather becomes one expression among many. Jupiter's enduring storm becomes another. Together, they show that the universe does not repeat itself. It explores possibilities, allowing each planet to follow its own version of order, balance, and motion.